Okay, I'm going to work through a linearization example by hand. We did this on class on Friday, and so this would be for those of you that did not see it because you weren't there, or those of you that want to just review the steps in this process. So look at my data set. The way this worksheet is set up is that um, the Y column says that this is your dependent variable in the instructions, and this is your independent, or your x-axis variable. So the first thing I'm going to do is just plot this. So I'm going to pause it, I'm going to plot it, and then I'll show you what it looks like. Okay, so there's points plotted, and we're doing this by hand, so I'm kind of estimating, and they're not exactly where they need to be, but they're close. I made my dots big because, I'm just estimating there, so I want them to take up some space. Now I'm going to connect these with a smooth curve. Whoops, that was not very good. I want it to go close to, but it doesn't have to go through all the points. So let me undo that one and try again. Okay, better. When I look at this, I can see that this is an inverse relationship. So I know from this shape that current is going to be proportional to the inverse of resistance, or the other way around, that the inverse of current will be proportional to resistance. I'm going to manipulate the resistance values. So I'm going to make a column that's equal to 1 over resistance. That would have units of 1 over ohms. Right, and I'm going to actually calculate these values. So this is what I'm doing to get my numbers. 1 over 100 would be 0.01 inverse ohms. 1 over 200, that would be 0.005 inverse ohms. 1 over 300, 0.0033, 1 over 400, 0.0025, and 1 over 800, that's equal to 0.00125. All those are in inverse ohms. Now I'm going to make a graph of inverse resistance still on the x-axis versus current on my y-axis. And that current, I haven't done anything to it, so those values stay the same. 1.23, 0.63, 0.37, 0.29, and 0.15. So this data will be plotted on the y, this data will be plotted on the x. Okay, so the first thing I'm going to do is set my scale on the x-axis. It's very different. It used to go from 0 to 800. That's what it was in the data set here. But now it's going to go from 0 to 0.01. So it's a much smaller axis because it's been inverted. Right, and this is going to, again, be 1 over resistance in inverse ohms. Okay, so if that's 0.01, this is half of that. Okay, and I'm going to keep my y-axis the same. I've made this 1, and then this would be 0.5, 1.5, and all my data will fit there. And that's current in amps. Okay, so my first data point resistance is 0.01, which is the largest value, and the current is 1.23. So 1.25 is about there, 1.23 is here. The next point, 0.005, goes with 0.63. So here 0.005, 0.5, 0.75, 0.63-ish is going to be around there. 0.033, 25, 3, somewhere around here. 0.033 goes with 0.37. So somewhere around here. And now I'm trying to follow this pattern. I can see it's starting to line up. So I can kind of get a better estimate of where it's going. 0.0025 with 0.29. So that's going to be a little bit above this point there. And then 0.00125 with 0.15. So that's right around here. Okay, and so now I can draw a best fit line that goes through there. So I would take a ruler out if I wasn't at a computer here. But since I am at a computer, I've got a best fit for a straight line tool. But you can do this with a ruler. You want to just get as close as you can to all the points. You don't necessarily have to go through any given one of those. All right, and then from that line, let's do it in a different color so it's easier to see. All right, from that line now I'm going to calculate my slope. I want to make sure I pick points off of the best fit line. I don't want to use ordered pairs from the data set. And to get a good estimate, I'm going to pick points that are far away from each other and points that are easy to read. So like this point crosses the grid line. That one's easy to read. And then this one does, and those are far away from each other. So my run is here, my rise is there, and now I just have to read off of my grid how big that is. You can see that each square on my grid along the x-axis is not a convenient number to use, so I have 4 blocks. 1, 2, 3, 4 blocks taking up 0.0025 units, and that's not a nice clean division. So I could go figure out how much each block is worth and then count these blocks and multiply. But I can see here that I've got 1 over here and then 3 over there, and together those make a complete span of this thing. And then if I look at the total there, I've got 3 complete spans. So without doing all that math, I can see that the run of this thing is 0.0075. And then the rise of this thing has 1, 2, 3, 4, 5, 6, 7 blocks. And again, I'm stuck with this strange division here. I know that going from 0 to 1, that's 8 blocks, so I'm just going to use that ratio to figure out the exact number here. So I know that my current will go up 1 ampere for every 8 units on the axis. And I'm only going up 7 units. So multiply 1 by 7. I'm going to get 7/8 of an ampere as my rise. And this is where you could go to your calculator to figure out what decimal 7/8 is. So that's 0.875 amperes. All right, now we've got our rise and our run. We can now calculate the slope. get a slope of 116.7 amperes over 1 over ohms. Okay, looking at this graph, it looks like my y-intercept is going to be approximately 0, and we could do some algebra to figure out exactly what it is, but estimating from the graph is good enough for our purposes here. When you need to know the actual value, this is where we'll be going to the software and letting the software quickly tell us what that value is. So now I can write my model. General format for the model should be y-axis variable equal to the slope value with its units times the x-axis variable plus y-intercept with its units. U-N-I-T-S. Okay. The slope units are always determined the same way. Slope units and y-intercept units are always determined the same way. Slope units will be rise units over run units or y-axis units over x-axis units. And your y-intercept units will always be the units of the y-axis. So, looking back at my graph, I know, get my pen back here, that my y-axis variable is current. My slope I determined to be 116.7 amperes over 1 over ohms. Those are my units. My x-axis variable is 1 over resistance. To that, I'm going to add my y-intercept, which in this case is 0, so I wouldn't normally have to write this. I just want to show you how this would look if that y-intercept were a number. 0 with its units of the y-axis, amperes. Alright, and then this is our mathematical model for the original data set. Alright, by mathematical model, I mean we could now use this equation to determine, we could use that equation to determine one value from the other. So, for example, given a current of 1.23 amps, if the current were 1.23 amps, I could figure out what the resistance would have to be by solving this equation. 1.23 and just doing some algebra now to solve for resistance. I can see that the resistance is going to be equal to 116.7 amperes over 1 over ohms times 1 over 1.23 amperes. Alright, that gives me a value of 116.7 divided by 1.23, 94.85. And the equation will also tell us the units, so the amperes here will cancel the amperes there, and I'm left with units of 1 over ohms. Alright, and if you know your algebra for simplifying fractions, you'll find that that's 94.85 ohms, which are the units of resistance. compare that 1.23 amps with a corresponding 94.85 ohms, and you'll see that's very close to what the original data set says. 1.23 amps here with 100 ohms compared to our 95. All right, and this is all done by hand, so you can see that this model, it's very good. If we could improve the accuracy of our slope calculation and our y-intercept, it would get even closer than it is. But note that it's very close. We're talking about maybe 5% error in this model that we did by hand. Okay, so that's the whole process of linearization.